Enabling safety switch. Arming UAV. Commencing Flint test. GCS, are we clear for flight test?
GCS is clear for flight test.
Commencing flight test.
Welcome to the Animus Ferus Flight Readiness Review. In the next 15 minutes, we will provide a summary of our team, our UAV, and the extensive testing conducted during development to prepare for the 2018 SUAS competition mission demonstration. Our competition team is made up of 9 motivated high school students. Dylan Turetsky, safety pilot. Vale Tolpagan, team leader. John Moxley, manual object detection, classification, and localization operator. Zachary Yin, manual object detection, classification, and localization operator. James Villamaret, competition viewer operator. Matthew I, ground control station operator. Rod Arian, obstacle avoidance monitor. Owen Krause, ground control station manager. Devin Host, safety officer. Spirit 10 is Animus Ferus' new UAV. It has been designed to be a significant improvement over the team's previous competition UAV, Spirit 9. Spirit 10 features a new propulsion system, a new autopilot system, a new communication system, a new electrical system, and a new custom-designed airframe. While Spirit 9 was built to complete the waypoint and air delivery tasks with high precision, it was unable to support the expanded mission task goals for Animus Ferus in the 2018 SUAS competition. Spirit 9's efficiency was maximized and performance was limited due to the underlying design of the system. Spirit 10's design removes these performance bottlenecks and is capable of exceeding the requirements established by the team. Spirit 9's core airframe couldn't support propellers larger than 16 inches in diameter because of both size and maximum thrust. To address this issue, Spirit 10's airframe is composed of larger, stronger carbon fiber pieces that support up to 18.5-inch diameter propellers. Extensive testing enabled the team to optimize the airframe's weight without compromising the integrity of the UAV. Spirit 10's propulsion system is more efficient and much more reliable than the system used on Spirit 9. The upgraded components provide a higher max thrust, resulting in enhanced wind resistance and improved maneuverability. Supporting the new propulsion system is a redesigned electrical system with full redundancy and a much higher maximum load. A new communication system provides 2 links between the UAV and the ground. An RFD 900X model provides an AES 128-bit encrypted communications link to the ground control station in the 900 MHz frequency band. An X8R receiver, operating in the 2.4 GHz frequency band, enables manual control. The enhanced autopilot system consists of Pixhawk 2.1 with dual GPS and compass modules. The autopilot features redundant sensor systems and redundant power supplies. Properly securing the LiPo batteries required the team to design a custom solution built from PLA plus plastic. The cases are designed to minimize vibrations in flight, improving the stability of the UAV. Finally, the payload plate provides a convenient mounting location for all payload elements. It was custom designed to be as lightweight as possible without compromising its ability to support the necessary components. To maximize the likelihood of mission success, the team applied test-driven development strategies throughout the construction of Spirit 10. Each component was initially unit tested, then simulation tested, and finally integrated and tested on Spirit 10. Overall, the team completed more than 200 hours of individual component testing. After the unfortunate things falling off aircraft penalty the team incurred last year, there was a renewed focus on reliability. A thorough analysis of flight logs and equipment revealed that a temperature-sensitive component failed in the air delivery mechanism, resulting in the premature release of the payload. To prevent a similar issue occurring with Spirit 10, each component was extensively thermally tested. This testing included simulating temperature increases, placing a maximum load on each component, and many flight tests in competition configuration. The testing results indicated that there is a high probability that Spirit 10 will operate nominally in prolonged exposure to temperatures exceeding 100 degrees Fahrenheit, reducing the likelihood of a similar penalty occurring during the mission demonstration this year. To ensure Spirit 10 is optimized at capturing waypoints during the mission, the craft was auto-tuned multiple times. Each series of auto-tuning improved the UAV's ability to maneuver with high accuracy and maintain control in non-ideal environmental conditions such as high wind. After completing the auto-tune process, the team tested the performance of the UAV in autonomous flight. In testing, Spirit 10 was able to successfully complete a full mission autonomously with no manual takeover. Overall, 40 autonomous flights totaling 20 hours were conducted, with 0 time spent in manual mode. To support the team's expanded goals and a reduced mission time, a new propulsion system was needed. Numerous thrust tests were conducted during an early phase of development to provide the team information about the efficiency and maximum thrust of each potential system. After analyzing the data, the team chose a complete KDE direct propulsion system because of the efficient design, high thrust, and low weight. The new propulsion system gives Spirit 10 an efficiency boost of 5% in optimal conditions over Spirit 9 and a 43% increase in maximum thrust. Spirit 10 is capable of autonomously capturing waypoints. Between both UAVs, the team tested over 300 waypoints, with a 99% successful autonomous capture and accuracy within 4 feet. As required by the SUAS competition, the team must display the flight boundaries, drone position, and all other competition elements. Created using HTML, JavaScript, and OpenStreetMap data, the viewer allows us to, in real time, see the movements of the drone and all obstacles. This is critical to keep the team and judges aware of our craft's movements, as this is the only component of our ground control station system that unifies all the active mission data. Building upon last year's work, we updated our custom-designed competition viewer to display more information with greater accuracy and increased reliability. Due to the essential information the viewer provides, the system was designed to be robust. In testing, it was able to gracefully handle an interoperability server disconnect. The obstacle avoidance program was a key component of the flight control system. Therefore, it was critically important to thoroughly test the algorithm. Testing the obstacle avoidance program was a multi-step process and involved using numerous different methods. First, all program components were unit tested to verify the development of the code. Next, the obstacle avoidance program was tested extensively in simulation, with attempts to avoid more than 200 obstacles. Once the obstacle avoidance program was ensured to operate nominally in simulation testing, the system was tested on the team's test UAV, Spirit 9. Finally, the obstacle avoidance program was integrated with Spirit 10 and underwent a final round of tests to ensure that the system was properly integrated into the UAV. During this final testing, Spirit 10 was able to avoid 85% of stationary obstacles and 50% of moving obstacles. To optimize performance of the imaging system during mission demonstration, the team tuned each component individually. The camera was tuned to provide high-quality images at the competition height, and the gimbal was tuned to optimize response times from the motors. The team then conducted simulated missions using custom-developed targets. These simulations provided the team with data used to determine the maximum speed at which Spirit 10 could complete the search area task without degrading image quality. This speed was determined to be 16 knots. Speeds exceeding this caused increased motion blur that reduced the quality of the images. After completing the aforementioned optimizations, the imaging system was capable of providing high-resolution images of targets with little to no motion blur. The detection and classification system consists of a manual target submission system and an autonomous target detection and classification system. The manual target submission system was tested by operators in simulated missions with targets created from plywood. The autonomous detection and classification system was first tested with unit tests. Next, the system was tested on over 100,000 simulated targets created by a synthetic dataset creator built by the team to use previous competition images to develop a full simulated competition image. Finally, the autonomous detection and classification system was tested with real plywood targets created by the team for simulated missions. The results of these tests showed the autonomous system detecting 60% of targets with 1 false positive. The autonomous shape classification was successful on 90% of detected targets, and shape and alphanumeric color classification was 97% and 80% respectively. The alphanumeric characters were classified correctly with 10% accuracy, and the orientation was classified with 20%. During manual testing, the team was able to correctly identify all target characteristics. The localization system was tested similar to the manual target submission system and autonomous detection system. First, the system was unit tested to verify the individual program components. Next, the system was tested in simulations with an average error of plus or minus 15 feet over 5 tests. Finally, the system was tested on Spirit 10 in simulated mission demonstrations with an average of plus or minus 30 feet acquired from 27 tests. The air delivery system was developed to provide a high-accuracy, low-weight mechanism for Spirit 10. Each component of the air delivery system was unit tested on Spirit 9, and finally tested on Spirit 10. During testing, the mechanism was able to withstand extreme temperatures and was wear-resistant. The final iteration of the mechanism was used to complete 14 practice deliveries with an average accuracy of 6 feet and a 100% success rate. Thoroughly preparing for the mission demonstration is vital for a high probability of success flight. To that end, Animus Ferus devoted extensive time to preparing for the mission demonstration through a combination of drills and practice missions. Each competition team member extensively practiced his or her role on the flight line to ensure that they are well prepared. Full mission tests were also conducted, which tested the team's ability to complete each mission task as well as their ability to handle certain component failures, such as if the ground control station or the backup pilot lost communication with the UAV. The UAV underwent 5 full mission demonstration simulations. During these simulations, Animus Ferus scored an average of 68% in the timeline task, 99% in the autonomous flight task, 56% in the obstacle avoidance task, 42% in the object detection, classification, and localization task, and a 97% in the air delivery task. Near the end of the team's second full mission test, Spirit 10 lost the motor and crashed. Although this was a very challenging crash and required a significant rebuild of the UAV, the team's analysis revealed a flaw in the autopilot. A poor auto-tune caused Spirit 10 to not respond to a motor loss properly. As a result, the team conducted a more aggressive auto-tune. After the fixes were applied to the autopilot, Spirit 10 was tested in a simulated mission that involved using only 7 motors, and passed spectacularly. Additionally, the team was able to gather key metrics about the performance and the limits of the UAV during full mission testing. For instance, through the mission demonstration simulations, the team found the maximum flight distance of Spirit 10 to be 8 kilometers, a delta of 7% from the performance measured in optimal conditions in flight operation. Autonomous flight. Will attempt. Confidence, high. Obstacle avoidance. Will attempt. Static obstacle confidence, high. Moving obstacle confidence, medium. Object detection, classification, and localization. Will attempt. Manual characteristics confidence, high. Autonomous characteristics confidence, medium. Autonomous localization confidence, high. Air delivery. Will attempt. Confidence, high. Team Animus Ferus expects to perform in the top 3 at the mission demonstration. Thank you for watching, and we look forward to a successful mission demonstration in June.